Let us discuss screw axes and screw operations. These are unique operations in 3D. By that I mean that they are in the 3D space groups. So, let me write that unique to 3D space groups, because they are not in, they do not exist in 2 dimensions, they exist in 3 dimensions, and even in 3 dimensions they were not part of the point group, and that is because they involve a translation component. So, here is the definition, that a combined operation of a rotation about an axis followed by a translation parallel to the axis is called a screw operation, and the axis is called a screw axis. So, because of the translation, it cannot be a point operation, and since both translation and rotation are type 1, this is also a type 1 operation, it will not change handedness. So, let us see this geometrically. So, we have a rotation axis, and let me consider a point in a plane perpendicular to the rotation axis. So, when we talk of a screw motion, I will first rotate this by some angle theta. So, we will get a point here, but that is not the image point, that is an intermediate reference point, because I have to combine it with a translation. So, I further combine it with a translation. So, this will be the final image point. So, this is the original point and this is the image point. So, the imaging process, you can see imaging process can be thought of as a screw motion, because it is rotation as well as translation. So, it is a result of screw motion. Now, why are we thinking of combination of rotation with a translation, this translation component here, this translation component was parallel, let us say translation toe parallel to the axis. So, why are we insisting on parallel? Why not perpendicular? Can we not combine a rotation operation with a translation perpendicular to the axis? In fact, we can, and in a space group this kind of combination is always possible. However, here if we have a rotation axis and we combine it with a translation which is perpendicular to the axis, this will result in rotation by the same angle. So, if there was a rotation by theta about this will result in rotation by the same angle theta about another axis parallel to the given axis. So, another axis one can imagine, and which will be parallel to the given axis, and the same angle theta will be there. So, this is equivalent to rotation by the same angle about another axis parallel to the original one. So, in this sense it is not really a new kind of operation, but just a new rotation about a different axis. We can see this as an I will not prove this, but let me just give an example, the simplest possible example, which we are already familiar with in our discussion with plane groups. So, let me consider a two-fold axis. A two-fold axis. So, if we have a two-fold axis in a space and I combine it with a translation which is perpendicular to the two-fold axis, then we know in plane groups we have seen this, and it will also be true for a space group, that this results in, so this is a translation, let us say this translation is to perpendicular. So, this will result in another two-fold which is parallel to the original one, but shifted to it by a vector t by 2, t perpendicular by 2. So, we are familiar with this case, and this will always be the case. It will not always occur at t perpendicular by 2, but somewhere in a space which can be calculated on the basis of the translation vector, there will be another axis about which same rotation is possible. So, that is why this case is not considered as a special, is not given any special name, it is just combination of two operations resulting in another operation, but this particular case is a new case for 3 dimensions and is given a name screw rotation, screw motion or screw rotation, and the rotation axis is called the screw axis, where the translation is parallel to the axis. Now, let us try to see what a combination of n-fold rotation and a translation parallel to the axis will give us. So, let us try to represent it in a sites notation. So, I write it as R n tau, R n is this rotation, n-fold rotation by 360. So, let us call that R n, and tau is a translation parallel to the axis. So, rotation, this is translation parallel to the axis. Now, let us see what will happen if I apply this operation 2 times. That is a square of this operation. Let me give an under bar to show that it is a vector, and R n is a matrix. So, this is a matrix column representation, and I am applying 2 such operators. Recall how we multiply the sites operator. So, the 2 matrices will get multiplied, that will be the resulting matrix of the product, and Rn will multiply with tau from here. The first matrix Rn multiplies the second vector tau, and then we add the first vector, which is also tau in this case. So, we get this as the product of our sites operator, which we have discussed in detail in previous videos. I am using round brackets here for sites operator. There is a little bit of variations in this case. In some of the previous videos, I have used square brackets, sometimes angular brackets are also preferred. In this case, I am just using normal parentheses, for representing sites operator. This comma also is sometimes replaced by a vertical bar, but I think writing comma and writing parentheses is simpler in this case. So, let us go ahead with that. And so, continuing with this product, this becomes Rn square. Note that tau, notice what is tau. So, tau is a translation parallel to the axis. What will this product be? Rn tau. Rn is a rotation and tau is a translation parallel to the axis. If you apply rotation to a translation parallel to the axis, it does not change. A translation parallel to the rotation axis is an invariant translation for that rotation. So, Rn tau will actually result in simply tau, and you will get tau plus tau. So, you will get Rn square 2 tau. You can continue this. Let us do one more multiplication. So, let us find out Rn tau cube, which is Rn tau multiplied by Rn tau square. We have already solved the case for square. So, we can write it as Rn square 2 tau Now, if I use our multiplication rule, so we get Rn cube Rn of 2 tau plus tau, and using the linearity of Rn over 2 tau, this is simply 2 tau, because if tau is a translation parallel to the rotation axis, 2 tau is also a translation parallel to the axis and will remain variant under the rotation Rn. So, I get 2 tau plus tau, which gives us Rn cube 3 tau. So, you have got the pattern now. When I squared it, I get Rn square 2 tau. When I cubed it, I got Rn cube 3 tau. So, now you can write the general expression. Rn tau to the power n. What will happen if I take an n-fold rotation, combine it with translation, and this combination I apply n times. So, this is what I want to find out. So, this will become Rn to the power n n tau. But notice that Rn was a n-fold axis, so it was a rotation by 360 by n. So, if you apply it n times, so the total rotation will be 360 by n into n. So, that will be by 360. So, R n raised to the power n is nothing but an identity operation. It is no rotation at all, or a rotation by 360 degree, which I represent by 1, which is our identity in international notation. So, I write it as 1, and n tau is the translation associated with it. So, that means there is no rotation. If I multiply a screw rotation, an n-fold screw rotation n times, I will get a pure translation parallel to the axis, which is n times tau. Tau was the intrinsic translation associated with. So, sometimes it is called, let me note that, sometimes intrinsic translation associated with screw operation, and sometimes simply it is also called pitch, just like we use it in engineering for pitch of a screw. So, this tau is either pitch or the intrinsic translation. So, n times multiplying or applying the screw motion n times results in a pure translation, which is n times the pitch, n into tau. Now, let us assume that R n tau was a symmetry operation. If R n tau was a symmetry operation, then this also is a n times applying a symmetry operation is also a symmetry operation. So, if the screw operation was a symmetry operation, then this left hand side is a symmetry operation. So, which means this is also a symmetry operation, but this is a translation. So, this has to be a symmetry translation. We do not use phrase like symmetry translation, we simply call it lattice translation. Lattice translation. So, this means that n times operation of a screw operation, n times applied, gives you a lattice translation. So, let us write this, n into pitch is equal to a lattice translation, and not an arbitrary lattice translation, because remember pitch is a translation parallel to the axis. So, this lattice translation is also parallel to the axis. Now, we do not know which lattice translation it is. So, if we have a screw axis, what we are saying, and we had a toe which was the pitch or the intrinsic translation associated with the screw, then we are saying that n times tau, it's some lattice translation, let us call that T, parallel to the axis T. since it is a lattice translation, it has to be a multiple of the minimum lattice translation in this direction. So, I write this as p times t min, where t min is the shortest lattice translation parallel to the axis. So, p in that case will be another integer. So, this gives us an interesting result that n times the pitch of the screw is p times the minimum lattice translation parallel to the screw, which means if I want to write the pitch of the screw, I can write it as p by n into t minimum. This is an interesting result. So, any screw operation will be characterized by a lattice translation which gives the direction of a screw, and also by this fraction, p by n, which finally gives that what fraction is of the minimum translation is the pitch. Of course, you can see here that the meaningful values of p has to be between n and 0, because if p is 0, then tau is 0, which means you have no translation associated with the rotation. So, that is a pure rotation axis. So, n is equal to 0 will not give us a screw axis, but a pure rotation axis. And if p is equal to n, then tau will be equal to t min. So, it is simply a translation. So, lattice translation. So, then you are combining a rotation with a lattice translation. That is a combination of two symmetry operations, which because of the group property of the symmetry operation is always possible. So, this is not a special case, simply a combination of an lattice translation. So, the special cases which give us the screw motion or screw axis are these cases. So, this is what will define the types of screw which we can have in crystal. So, it is defined by, we have seen two integers p and n with p less than n and greater than 0. The possible values of n we have seen are 1, 2, 3, 4 and 6. So n is of course a one-fold rotation is an identity, and if I combine it with translation I will get a pure translation. So that's not a screw. So 1 plus will just give me translation. So not a screw. With 2, the only value of p possible is 1. So I will use the notation 2 1 to represent this screw. So a screw for which, let me define that. So a screw operation with n toe is equal to p toe min is what we established, is what is correct. So this is designated as NP, NP screw. So for two-fold, the only value possible for P between 0 and less than 2 is 1. So I get one possible screw operation 2 1. For 3, you can see that we will have, now the values of P can be 1 or 2. So I have two kinds of axis, 3 1 and 3 2, two operations. In case of 4, we have 3 values, 4 1, 4 2 and 4 3. And for 6, I will have 5 different screw axes, 6 1, 6 2, 6 3, 6 4 and 6 5. So if you count, these are the 11 screw rotations which are possible in a crystal. So let me give you a table of graphical symbols which are used to denote this in international tables. So screw axis, we can call the symbols which I have just given you alphanumeric, symbols, and now I also want to give you the graphical symbols. These are used in when in international tables the space groups are represented and their symmetry elements are shown. So those graphical symbols will be used. So 2 1 screw is just, remember the two-fold axis. Two-fold axis had this symbol. I just have to extend this two sides to make it a screw symbol. Then 3 1, for the three-fold we use triangle. 3 1, we extend the sides of the triangle to represent a screw. 3 2, we again extend the sides of the triangle but in the opposite way. That's 3 2. 4 1, 4-fold is a square, and I extend the sides to represent 4 1. 4 2, only two opposite sides are extended to represent 4 2. 4 3 again all sides are extended, but in the opposite sense to 4 1. And finally, for 6 fold we have the 5 screw axes 6 1, 6 2, 6 3, 6 4 and 6 5. 6 fold is represented by hexagon. And you extend the sides to represent 6 1 screw. Six two screw, you extend the alternate sides. So only 3 sides. In 6 3, only 2 sides, the 2 opposite sides. 6 4, again 3 sides, but in an opposite sense to 6 2. And 6 5, all the sides, but opposite sense to 6 1. So these are the graphical symbols which are used in the international tables. Just a comment here that 3 1 and 3 2 are actually mirror images of each other. So they are enantiomeric pairs, that is, they are opposite handedness. So if you reflect 3 1 in a mirror, you will get 3 2. So they have opposite handedness. Same thing is true for 4 1 and 4 3. So they are also enantiomeric pairs. In the case of 6, 6 1 and 6 5 are enantiomeric pairs, and so are 6 2 and 6 4. So in fact, that is why the notation of using opposite extension, which I was showing you, that the arms are extended in opposite sense, is to show that they are mirror images of each other. These are also mirror image pairs. 4 2 is left and 4 2 is achiral, thus does not have handedness. So if you reflect 4 2 in a mirror, you will get the same 4 2, and this happens here in 6 3. Achiral, and 2 1 is also achiral, does not have handedness. Two-fold screw sometimes lie in the projection plane in international table, and for that there is a special symbol. So if the screw axis is lying, all these symbols which I have shown you are for screw axes lying perpendicular to the plane. But if the screw axis lies parallel to the plane, then the symbol shown is by a pair of half arrows. So I think for the moment we will end our discussion of screw axes here, and we will discuss more later. Thank you.